And so I see. Okay, we got that. Thank you. All right. Well, good morning, everybody, and welcome to the Railway Application Section webinar for June 2025. This is a special edition of the webinar covering the 2025 problem-solving competition sponsored by TTX. My name is Marty Schlenker. I am the Vice Chair of the Railway Application Section for the year 2025 and co-host or co-chair of the problem-solving competition with my colleague Masood Kang, Dr. Masood Kang of TTX. Your presenters today, our bios are on the screen here. I will be doing a brief intro on behalf of Informs, and then I will turn it over to the subject matter experts of the problem-solving competition, Dave Cannon, Masood Khan, and Roshan Manibharathi from TTX Corp. So I think we are at 3 minutes after the hour. Ely, how many attendees do we have on the line at this point?
In the Zoom,
Yes.
we have
Okay, like
25
25, right?
members. Yeah.
Great. All right, well, thank you. Let's move forward and begin with the content today. For those of you who may have found out about this competition by LinkedIn or Kaggle itself or any other means, a brief introduction to Informs. The Institute for Operations Research and the Management Sciences is an organization that you should consider becoming part of if you're not part of that organization already. We have 13,000 members across the world. In addition to the general subject of optimization and analytics, AI techniques, we have specific domains that are of special interest to applications and techniques within this broad field. The railway applications section has been around for more than 30 years and is populated by railroad professionals on nearly every continent, applying optimization and AI-based techniques to railway operations and railway safety. The problem-solving competition, sponsored by TTX in the year 2025, has occurred annually since 2010. And if anybody is interested in the history of the problems and the results, we have a link in this presentation that can be followed. Go ahead to the next slide, Ely. Thank you. To reorient everybody to the timelines of the 2025 problem-solving competition, the data has been available to competitors since April 4th, including the Kaggle site and the instructions for registration. Today is June 11th, our webinar. We have open registration for new teams that lasts another 6 days until June 17th. We will take questions and answers via the Kaggle discussion site until August 19th, which is the solution submission deadline. The Kaggle site does include the instructions for what constitutes the submission to be considered to become a finalist. A judging group will identify the finalists by September 3rd and notify them. At that point, the finalists will be asked to create a video presentation to accompany their paper and their results. Those video presentations will be judged during the week of October 6th through 10th, and then the results will be sorted, and the nominees for awards will be announced October 26th through 28th at the Informs annual meeting. It is our great hope that the finalists will be able to attend the annual meeting live to perform a final presentation before the announcement of the winners. Teams that do well should consider making plans to attend the annual meeting. And it is, of course, our desire also to have as many of you as possible become longtime contributing members of the Railway Application section of Informs. Those of you who have submitted results to the Kaggle site already, congratulations on your progress. For those teams that have not yet submitted results, it is absolutely encouraged for everybody to dive into the problem, to have a look at the really comprehensive and rich data sets that were provided by TTX company and to get to work. This is a complicated problem And in addition to just the basic analytic challenge, we also have given you a data cleansing challenge to go along with it because this is real world data. And so it is never too early to start working on this. You have until August 19th, not only to create results, but to create a paper describing your methods. So there's not a small amount of work that is required to be considered for the awards, but the awards are very richly compensated too. And so I think this is a really strong competition, and so everybody should put their best into it. Um, let's move ahead, Yili, to the next slide here. For any attendees of this webinar who have not yet registered their teams, this is excerpted from the instructions that are found on the Kaggle site for this competition. There is the email address to which you would notify us of your intent to compete. Subject line should be RAS PSC 2025. Tell us about your team, who your members are, what your affiliation is, and send your contact email addresses, and we will respond with a link to the data sets in the full site that is available on Kaggle. Do this by June 17th, and then you will have 2 months plus a couple of days to compile your results and your paper. So we encourage everybody to do this, even the competing teams. If you believe that there are uh, potential people out there who have not yet registered, who don't yet know about this competition, who would be worthy competitors, please do spread this information to them so that they can also join this competition. All right. With this, I would like to end my portion of the webinar and hand it over to my distinguished colleagues from TTX Company, David Cannon, Masood Khan, and Roshan Manibharathi. David, it is your time to share slides and proceed.
Thanks, Marty. All right, let me bring up. Is everyone able to see my screen?
Yes.
All right. Well, yeah, thanks for the introductions, Marty. And I just wanted to thank you for helping us facilitate this and giving us the platform to present the problem. A big shout out to my colleague, Masood, for all of his work preparing the data and laying out the problem in a succinct format. So huge thanks to everyone involved. So the way we're going to lay this out is pretty high level and pretty broad. We know everyone comes with different backgrounds in terms of skill sets and knowledge of the rail industry. So we intentionally left it that way and are intentionally leaving some time for Q&A. So if you know a lot of this information already, I apologize, but it should be a decent background and setup for the approach we're taking. All right, so Marty already covered our introductions and you can see our bios there, but we'll set some groundwork for who TTX is, our business context, where we're coming from, some of the engineering principles involved with this data, some of the challenges that we run into with the data, some hints on the competition, and then, like we mentioned, a lot of time for Q&A. And I would also like to preface, this is a real world problem. We're excited to tackle this. So the data is messy, but this is something that we are actually working on. It is not just a theoretical exercise. So we're very excited to see what everyone produces as a result of this.
David, could I interject a second?
Please.
Um, Unlike some of the theoretical exercises that are performed in student competitions, success here, I think, it's fair to say, will qualify you for success in the industry as an analytic professional. This is not easy. And so, give it your best shot. I can't say that enough. Back to you, David.
All right. All right, so a little background in terms of the business context. Who is TTX? Where do we fit into all of this? So we are a rail car pooling company, which is different from a leasing company or a railroad itself. We are owned by the major Class 1 railroads that you'll see on the bottom of the screen there. And we collectively manage and maintain a fleet of 177,000 rail cars. We produced $1.8 billion in revenue and have over 2,000 dedicated employees across our network over North America. Um, what this allows us to provide as a pooling company is kind of unique fleet size planning ability, and this is granted to us by a limited antitrust immunity from the Surface Transportation Board. We perform full rail car maintenance and repair services on our cars, and are really more and more positioning ourselves as a data and information planning company in addition to just owning the assets. Some of the benefits that this system allows us to have is really, I mean, first and foremost, reducing those empty miles. So when TTX, when a fleet, Class 1 railroad will send a load through one of our cars, and then it reaches another end of the country, rather than having to send back an empty car to be able to exchange it, another road can pick it up and then fill it and send it back. So we're really reducing those empty miles. There's less switching operations. There's capital outlay avoidance. We are able to mitigate risk and kind of standardize our fleet to really best serve our customers and make more reusable assets in the process. So to dive into that a little bit more, some of the operational and financial benefits of railcar pooling. So operational efficiency, capital avoidance, and shared risk are the three kind of pillars of that. But TTX pooled fleet cut empty car miles, saving the railroads approximately $345 million in operating costs each year, as fewer and fewer cars are doing more and more work. This continues to grow over time. So we also have unique storage provisions that have saved the roads approximately $160 million in car hire costs, for example, in 2024. And we're really moving to standardize high capacity rail cars, get away from, very specific, unique designs to more designs of cars that are usable across many different operations. So TTX handles all of our own repair operations as well in um, f- far in excess of what a full service lease would look like. So we're really able to turn up the amount that we are maintaining our cars to a very high standard, and you'll get into that basically with the problem set that we're laying out here. But in terms of capital avoidance, we obviously own our rail cars, and so that the railroads do not have to. So that means about $17 billion worth of assets. And to maintain that, we spend around $900 million a year in our annual maintenance, of a very large portion of that being wheel sets. Um, Hence the set for the platform for our problem here. So capital improvements are made to ensure that our continued fleet relevancy and efficiency are maintained over time, and it really eliminates the depreciation expenses from falling on the roads themselves. By sharing this risk, then, and pooling our rail cars, we can mitigate across the network as business needs is shift over time and as the market changes. So it really allows us to be flexible and provide this pooled fungible cars to improve utility and reduce costs for the roads and their customers over time. All right, so diving into a little bit more of where the hypothesis starts for this, and again, many of you probably are very well versed in this type of thing, but the value of predictive maintenance, setting the stage for this problem set. So we've kind of outlaid the different approaches to this, kind of in increasing sophistication from top of the screen to the bottom, but kind of the basic approach to the maintenance would be run to failure. So you just run your rail cars. When the components fail, you set them out and you replace. Obviously, there would be some pros and cons to this, right? So you would need absolutely no analytics in this kind of mindset or in this kind of approach, and you're completely consuming the parts that you have on your cars. Huge downsides being those large downtimes, obvious issues with safety and concerns with that, and a really unreliable, totally unpredictable fleet. So then you kind of get into the idea of preventative maintenance. This is kind of an approach that TTX in the past had pursued for a long time, where essentially you just have mileage frequencies where you wholesale replace parts on a car. So, for example, a car would run for 1 million miles, and then you kind of do this sweeping overhaul of many components. Again, there are pros and cons to this approach. So you really don't, minimal data collection would be needed, and it reduces downtime significantly from the run to failure approach. But the negatives are that it costs a lot and you're likely wasting a lot of remaining useful life on those parts. So parts do not fail together. They have very different timelines of when they fail, different costs. So by doing this, you're kind of just assuming that everything needs to be changed out at once and that they have no effects on one another in terms of importance for reliability of the car. So then we moved into more of the condition-based maintenance, which is kind of the stage that we're currently at as we evolve towards the final stage of predictive maintenance. But we're kind of in this condition-based maintenance strategy where either through known mileage thresholds or certain intervals of inspection, components and particularly complex and high value, high safety impact components can be uh, inspected through work orders generating, and then should the maintenance specialist deem it appropriate, the part would be replaced, and then the car could return to service. So a huge benefit of this would be improved lifespan over the preventative maintenance, reducing the waste of component replacements. But obviously, then, this may be suboptimal. So you're still kind of in this rules-based approach. If you're using various mileage thresholds, it may not be a very dynamic or changeable system that you're in. And you're relying on just these inspections that may be triggered at unoptimized thresholds. There's also a risk for premature failure in this subset if you don't have those intervals tuned correctly. So that's where we're kind of migrating towards the true predictive maintenance approach, which essentially would just be you are making the optimal predictions on components and being able to fire work orders dynamically in terms of when you're changing out these components on cars. So this kind of approach would allow you to have optimal lifespan of your components and truly minimize your downtimes. The negative or the challenge, I should say, would be you have to have a system in place which makes very accurate predictions and a system in place which allows you to act on those predictions, which is a huge component of this. You can have the most sophisticated modeling in the world, but if you can't take action in a time that is feasible for using that, then it doesn't really matter, right? So that's kind of where we're positioning ourselves in this final stage here. All right. So again, like I mentioned, we put this on here as a little extra background for those who may be less familiar with the rail industry or rail car trucks, as we refer to them. So apologies if you know all this already. But here is a illustration of the classic three-piece North American freight car truck design. There are many different designs that are out there, but this is arguably one of the oldest and most reliable designs, and for good reason. So you can see it's basically made up of two wheel sets with a center bolster and two side frames attached on the outsides of the bolster. Um, should be noted, these components are essentially just held down by gravity and interact with each other through friction, which is kind of mind-boggling when you first think about that, something so massive moving down the track, that they're not really bound together in any other way than that. So that center plate you see there on the top of the bolster is where the truck is coupled to the rail car body itself. And then where the bolster reaches through the two side frames, they interact with some sort of system of springs and friction wedges. These wedges basically control the stiffness of the truck as it navigates down the track. The side frames are designed to have that compression member on the top. So as the two wheels are putting vertical forces on that top compression member is compressed, and then the bottom of the side frame is the tension member. So essentially, this is the very high level layout of what a truck looks like. There are, like I mentioned, there are different designs for different purposes. There are what you'd call premium trucks that provide additional benefits and can reduce some of the hunting or other performance attributes that would be measured. But there may be downsides with cost or other high-speed performance issues like that. So there's a wealth of resources available to read about this, one of which is linked down here. So I'd encourage you to do so. All right. One other engineering principle or background that we wanted to provide was the idea of wheel wear. So what you see here are some of the common measurements that would be taken on wheels. On the left side there, you see a profile of the rail car wheel and some of the different measurements that are on it and defined in AAR and FRA documentation. So there is the flange width, the flange height, the rim thickness, and tread hollow. You can see on the right a superimposed lines for what a new versus a worn wheel look like. So this is just an example of one wear pattern, but the blue line would be a fresh, brand new wheel, and then the red would be a worn profile where you can see it got that internal flange wear, the tread hollow, so tread wear on that center portion of the tread. And this would be an example as it interacts with that railhead over time, wear patterns that could occur and result in condemning criteria, which Masood will touch on a little bit later. So again, there is quite a bit of documentation on this that we would encourage you to read and investigate as you get into the problem set and understand the context of the data. All right. So where is some of this data coming from? A lot of it is from wayside detection systems. So across the network of North American railroads, there are a series of wayside detectors that are implemented in the track that capture various properties about performance of the trucks, specifically with the mindset of safety. So these are several sets of them, but let's begin at the top. So wild would be the wheel impact load detectors. This would be a basic strain gauge network of detectors at various sites across the North American railroad system that capture vertical impact forces exerted by the wheels onto the rail. And then there's various subsets of readings that the actual data contains, but at a high level, this is what it is. There is THD detectors, truck hunting detectors. So again, these are strain gauge based detectors that capture lateral oscillations of the rail car truck as it passes over them. This is output in a unitless measure called hunting index, which is from 0 to 1 and is basically it is a algorithm that has used the lateral forces generated from the strain gauge reading to output a hunting index, which is a measure of how much the wheels are oscillating back and forth on the track. The AEI detection system. So this is automatic equipment identification. It's an RFID based system where the cars have a RFID on the side of them as they pass by the readers. The information is captured in terms of location and equipment information, and is basically the source for all location information that you might see in some of these data sets for mileage, for example. There is hot bearing detectors, which I believe are one of the oldest wayside detection systems that are around. They are an infrared-based detector system for measuring the temperature of roller bearings. This is very key for safety in the industry to detect early signs of catastrophic wheel failure or catastrophic bearing failure, to be more precise. Finally, there's two more, but we've included in our data set just one of them. So WPD, wheel profile detector. This is a laser-based detector system that measures wheel set geometry and gives some of the measurements on the profiles of the wheels that I showed in the previous slide. Finally, there are truck performance detectors, which again are strain gauge-based detectors that are used to evaluate suspension performance, again by measuring vertical and lateral forces. So you'll notice a lot of these are strain gauge based sensors that measure forces and then do something with that information. Like I mentioned before, there is a wealth of resources to read here. I've linked two of them from the FRA that go into great depth about what these are actually measuring and some of the calculations that are built on top of that. I'm going to pass it off to Masood, my colleague, to talk about some more depth on the data.
Yeah, thank you, Dave. Do you want to keep, a screen share, just, walk through that your slides,
Sure.
if that's fine.
Yep.
So, here we are going to, deep in, dive into those, each data we have in our problem competitions, problem solving competitions. We start with, wild data. From each detector, may generate multiple, columns, but for the sake of simplicity, we decided to bring, a few of them here. For example, from wild data, we brought only, average vertical and maximum vertical forces. As Dave said, EHMS system, coming from Railink, they mentioned a couple of like the levels for each, detector data. And for the wild data, we have 4 levels. As you can see, based on the ranges from like 0 to 65, units of force. We decided to label them as label 1, 65 to 80, label 2, and then so on and so forth. I believe these levels are defined based on the maximum max vertical forces. But we don't bring those, levels in our data. It would be it would be something when you wanted to kind of, do the feature engineering. For example, you can create categorical, features out of these, 2 columns. So Dave, could you go to next?
Yeah, and just to add one
Yeah.
piece of context, for those who might not be aware, these EHMS, like Masood mentioned, these EHMS levels are not included in our data set, but we thought it was relevant to set the stage that there are defined levels within these detector thresholds that mean something. So to add a little more context, the level ones are non-actionable window open alerts. So that just means it's an advisory state for the detector to have reached. And then as you get down further, they get into what would be called like condemnable alerts. So that's when you can read those descriptions, but then when they might be specifically or mandated to be actionable as a result of the detector reading.
Thank you. So the wheel profile data, we brought only wheel diameter and wheel width. Something, it would be, good to notice is that, some of these, metrics, you may not have, any sense, but some of them are like, for example, for the wheel diameter, it's good to know that, the wheel diameter could be something from, I guess, 28 to 38 inches. So if you see anything out of this range, you can simply notice that this is coming from the, an outlier, because those detectors may generate, noises. And then, so it would be nice, to have some sense about those data. I believe I brought most of them from one size wheel, but if you see anything, above that threshold, you can simply ignore that or just, try to impute those data. Yeah, next, please. So for truck hunting data, again, we have those levels defined by the AR. I mean, basically, we have only level 1 and level 3, but in our group, we decided to add another level, which is level 2. We have these, 3 columns in our data: level 1, level 2, level 3. This is the way, we define those levels. If truck hunting is from 0.2 to 0.35, it's level 1. If it's from 0.35 to 0.5, it's level 2, and then above 0.5 is level 3. And then in the raw data, most of the time truck hunting can be either, from -1 to 1. So we take the absolute value, but I believe for the, make it simple, we already, take the took the absolute value of hunting index and put it in our data. And then as you can see here, these are the truck level data. Those, the other data sets we have that are wheel-based data, but as Dave showed in that picture, we have two wheel sets, which is showing like four wheels on left side and right sides for a single truck. So you may see that, for example, for a single truck, we have we have four, wheel profile readings and four, vial readings, but only one truck hunting, readings because it's coming in from the truck level. And then the other data you may see in the truck hunting data is train speed, and also we have the percentage load and the left-right imbalance. Again, for the train speed and percentage load, you can use your judgment. For example, percentage load cannot be above something, but sometimes because it's calculated, you can just simply define a cap on it. You don't need to drop those records. For example, if it's above I don't know 200%, you can put a cap on it. You don't need to drop those records. But it's nice to know that, for example, this range should be something about like, 0 to, I guess, 150% or something.
Masood, the very fact that you have an index that is being represented in this data indicates it's already gone through a transformation from the raw sensor readings that these detectors take. And I think the index is a relative representation of the side-to-side movement that the THD measures. Is that correct?
Yeah.
Great. Thank you.
Yeah, couple of clarifications. Level 1 is not a AAR condemnable event. It's a window open, like it's written on the top right. It's level 2 and level 3, which are condemnable, and you can read what that definition is. Another quick clarification is, we have been talking about the truck a lot, and all these THT levels are for the trucks. But you need to understand that one car can have a minimum of 2 trucks, up to 6 or more. So there cannot be one truck per car. So you might see a single car with multiple trucks in it, but each truck has its own hunting index number.
Right.
Yeah. Thank you, guys.
Thank you, Roshan.
So potential, errors, I covered most of them, but you may see that, the axle numbers may, capture, may detector actually capture those numbers, wrong, because basically we have axle numbers from 1 to 8 in our data set. But if you see anything beyond those, records, you can simply, omit them. And then to your point, Roshan, to make it, simple, I use only, 3-unit articulated, connector rail cars. So you can assume that each car has, 3 units, and then those, intermediate truck units, they have a shared trucks. So we have 3 units, 4 trucks, and 8 axles for all of the, equipments we have in our data. And then about the added mileage, because the added mileage coming from another source and it's 3 months behind. So you may see that, we have, I guess for the month equipments. So just note that it is coming from the, shortage in our data. I would say, you can simply, try to figure out a better way of handling that, because when you wanted to do the model evaluation, you may see some errors because it assumes that, your equipment does not have any, mileage in those months. Supplier code, vendor supplier code may be missing in some, records. And also we have missing values in other, columns. Just, try to do the EDA first and try to impute those, missing values. Then, go for the modeling part. And then just keep in mind that those, reading data may have, outliers and anomalies. They are not perfectly, good data. So these are just, the thing we mentioned as the potential errors. Dave, do you want to add something here?
Uh, no, I think you pretty much got it. Thank you.
Good, good.
Masood, can I
Yeah, sure.
thing about the data? And it's less about the errors and more just about the structure. So with these rail cars, not all of them have four axles, right? Because we have one ID, then may have one or we may have more than one platforms. And then within that we have two or more than two trucks. But it is the case that in this data set, all of the trucks have two axles, and each of the axles has two wheels. Fair?
Yeah, yeah. I try to make it, simple.
Very, very
Appreciate it.
fair. Yeah.
Thank you.
Okay, this is the overview of our data set. You can see that we have different sources on our Kaggle website. The data web page, but we didn't actually, merge them together because, as I said, the main part of this, competition would be how to, combine these data set together and then how to, extract features from those detector data. We have the failure data ready. So we have like on a monthly snapshot, we have the mileage on each wheel, and then we also have each column shows like if it's failed in next 30 days and what was the reason for that failure. And then our goal is to design a model that could predict the failure reason in next 30 days. So you can simply ignore wild data, WPD data, and truck hunting data, but it doesn't give you anything if you train that model because we tried that. The model cannot be as good. So our goal is to somehow digest data from wild, WPD, and truck hunting in a way that we can combine them together. And then one of the main challenges here would be because this data are coming from detector that installed on the site, not on the car, you may have, sparse data. For example, for a single, truck location, you may have like, some wild data, but nothing about WPD or truck hunting, or you may have only, truck hunting data for some weeks. So this is, one of the, challenges here. We do have dates, but they are not synced because if a train, if actually a rate car passes one, detector, we have data. Otherwise, we have nothing. But for the mileage data and the failure data, we try to have like all those monthly snapshot data. So you can assume that we have every month we have mileage data for those equipments, and then we have also those wheel failure, but we may not have those truck hunting, WPD, and wild data. And then the other part, as I said, truck hunting, it's at the truck level. So if you wanted to join it with the wheel failure data, you can use the equipment number and truck. But for the WPD and wild data, because it's at the axle site level, so you need to merge them based on the equipment number, truck, axle, and side. Yeah, Dave, could you go to the next one? So here I tried to bring two approaches. These are just examples. You can bring your own approaches. But the thing is that when it comes to the detector data, one of the most common method would be signal processing. So assume that this is one of our detector data, which is the hunting index for a single truck. So in the signal processing, the way they handle the problem is like we define one X window, which is like we can call it a look back window, and then you would calculate all these metrics for that window. For example, I would the gray area is like my X window, and then I can simply calculate these metrics. What's the average, what's the max, what's the peak to peak, RMS, variance, standard deviation, power. Most of these metrics you can find them. These are designed in any signal processing, which is coming from MATLAB because MATLAB was a powerful tools for signal processing, and back then they have a solid package for that, and it generates all these features. But the good thing is that you can simply find similar function in Python, and then recalculate all these metrics. And then the way we use it in our problem Yeah, Dave, if you go to the next slide, it's for example, we have input data, we have hunting index, training speed, percentage load, etc. And then we for each metric, we define that window, and then we calculate all these measurements for that. For example, we have what was the mean of hunting index, for example, in the last, I don't know, 30 days or 60 days. That window, it's up to you. You can make a narrow window or very long or wide window, and then you can see that it generates more features out of those single input data. And then this would be your X window, and then your Y window. This is coming from an example, but for you it would be different. Your Y window would be the failure reason in next 30 days. So you can simply define a classical, multi classification, machine learning project out of this data set. The other approach would be LSTM. Conceptually, it does the same, because you have the X window and Y window, you have the look back window, and then look ahead window. But the thing is that this time I don't aggregate my data. So it's like, for example, let's say I have percentage load, left right imbalance truck, and then hunting index, and then I define, for example, last 60 days as my X window, and then I took all those data in one array, and stack all those arrays on top of each other to create a 3D tensor. This is an input for the LSTM model, because if you have experience with those LSTM models, you can create your input data in any dimension you want. You don't have to make it like a table. So the LSTM makes it possible for us to input the raw data with no aggregation, and then the same story for the for the Y data. Here we have only one label, but let's say if you have like 4 different measures, so your X for your Y actually data set would be again a 2D, which is like for each label you have 1 columns. And then I added some good examples. You can find them here also in the Kaggle web page. I added those as resources. One thing you may notice here, I put it here as a step, not time or date. This is one thing they do to make these sparse data sets possible to aggregate, actually, because the thing is that you can ignore the date time and then just count the number of records. For example, I would say take the last 60 records I got from the truck hunting, last 60 records I got from the WPD, and last 60 records I got from the wild data. So it makes it easier to code, but again, it may not be correct, because you're putting data that are not coming from the same date next to each other. So the other thing about LSTM, you may need to take these steps. You can find the same steps in the code example I provided. It'll start with data preparation. When we define the time steps, it can be either the date, or you can define your own time step, like 1, 2, 3, and then you define the cycle, which is coming from one failure to another one, and then using that cycle, you define the remaining useful life. I think up to this point, we have those remaining useful life. You don't need to do it, but when you have those data, you need to create a tensor. So we define the look back window. And again, you can pick whatever you want as your number. And then we need to transform those 2D tables into 3D tensors. So that transform feature, you can find the functions in the code example I provided. And then finally, we define the labels in a way that is compatible with that LSTM model, which is coming from the window, look ahead window. And then you don't need to define a new look ahead window, because our goal is to predict next 30 days failure.
All right.
And yeah, that was it.
Perfect timing, guys, for the entry into the Q&A. Thank you very much for this. And so, competitors, what questions do you have?
Okay, I will ask a question. Can anybody hear me?
Yes, if you can go ahead.
Yeah, thank you. So the actual question is, you should have some kind of benchmark, right? Can you share, not the best one, but more or less what we should aim for, metric-wise?
Sorry, could you repeat your question?
Yes. If you have some kind of a benchmark for the metric, and I don't mean something state of the art, but something good enough so that we can have a sense of how well we're doing.
Yeah, if you're talking about the model benchmark, I can say, you can simply see those, other competitors, results in the public, team board, which gives you an idea, for example, how good or how bad your model is. But if you wanted to see the benchmark for each, individual features, we try to cover most of them in this, presentation. For example, the range for the train speed, range for the hunting index, any data we have in our data, we try to put a range on it. But I don't know if you're looking for other, benchmark for your, modeling.
So
Yeah, what
let
I
me,
meant, yeah.
go ahead, Evgeny. Go ahead.
No, I wasn't talking about the range of the variables, of course, but about the some kind of score that you hope for. Okay, what score do you hope to beat?
Yeah, as I said, you can see those. This is a good thing about Kaggle. Honestly, we don't have any, score in our mind because it's coming from the log above point, I guess 85 would be, useless because it's if you pick a random model, it generates 80.85 as a score. But if you go to the Kaggle page, let me see if I can show you an example here. Can I steal the screen for a sec? So can you see my screen now?
Yes.
Yeah. So if you go here in the public scoring, you would see, the score here. So I can say, any score, something I try to create a random model, with no for training, just try to see what would be the score, and then it just submit a result and results to the Kaggle. You would see your score, and it gives you an idea. For example, it's good or bad. But the thing is that this is not the final score. It's only coming from the public result. As you can see here, we have 77% of the data is coming from we use for the public. And then we also have another 33%, which is not, available at the moment, but we calculate those score and then we use that as the final scoring system.
Masood, we should also mention that the criteria for selection of finalists is not based on the numeric scores alone, but also on the quality of the paper that it accompanies them.
Exactly. Yeah.
All right, we have a question in the chat. In wild and WPD data, train dates do not match. Can you please explain why they don't match?
Do you want to answer that, Masood, or should I?
You go.
Yeah, essentially because of the issues that Masood was outlining. So those are coming from two different detector sources. So there's no guarantee that set of wheels went over the wild and the WPD site on the same day. So there can be very different frequencies of these readings occurring on a given wheel set.
Yes. Each of the railroads of North America makes their own choices about where to put detectors and which ones to co-locate with each other.
And maybe it would also offer some context, like Marty was alluding to. So we have no control over the detector site locations or the maintenance thereof of them. And so that lends itself also to some of our challenges with data cleanliness. We have very little input on that process.
We also have a fleet that is made up of cars that are in continuous high mileage service, and whose utilization trails off from that, where you may have intermittent periods of storage, where you would have no readings, no mileage being accumulated. So you've got the whole gamut there. And whether mileage alone or mileage plus time, may be a factor here is for the competitors to determine.
Yeah, just one note. I remember, it was in the QA session on the Kaggle website. One of the data sources, has problem in the date column. I remember, I replaced that. If you see the same problem, I guess you just need to download the new version. It was like maybe months ago, but I can't see the QA in the discussion. I think the guy maybe dropped that question. But I remember, they mentioned that, and I revised the data, and I also replied to them.
I think I asked you that question, but since then I have a new account, so
Oh, okay,
probably
that makes
it
sense.
was dropped automatically.
So another question in chat. Yes,
Man,
the idea is to merge WPD while and THC data with the wheel failure. You can either go with the signal processing approach or the LSTM approach.
may I ask a question?
Yeah, sure.
First, thanks for your presentation and your information. I appreciate that. Dave mentioned that for the maintenance, there is different, strategies. For example, preventive maintenance, condition-based maintenance, and predictive maintenance. Okay. And he mentioned that now we are on the condition-based maintenance. Okay. Just I'm wondering, all of this data, were calculated based on this strategy, or some of them they are coming from the preventive strategy.
I would say so I guess I probably should have clarified our condition-based maintenance strategy does not apply necessarily to wheels. So the unfortunate reality is that wheels are failing at a much lower mileage frequency and are changed out much more heavily than some of our larger and more complex systems like the bolsters and side frames. So the wheels, I guess, essentially are on a run to failure or a more so like that currently. But we
Okay,
are
great.
looking and evaluating as part of this project to move to a predictive strategy.
Okay, great. Thank you.
That's a good point, Farzan, because
Yeah, great point.
yeah, our data is not, manipulated by our policy yet. But the thing is that you just keep in mind that it comes with the human error because we've sent a guy for example, in a shop, a guy would gauge those, wheel diameter, and then they decided to replace a wheel and then put a failure on it, and then define, the failure type. So if you see anything that is not matched, for example, we have three, I guess, four different type of failure. For example, we have high impact or thin flange or high flange, a failure, and then you see that it's not. I mean, the other data cannot. There's no correlation between these data, so you can assume maybe the failure reason it's not, actual, but it's not something, general. It's a possibility.
Okay, thank you.
Yeah.
Thank you for the explanation.
Another question in the chat. Given that wild has 3 levels, in practice, once we get the 80 kip alert, does it make sense to predict the 90 kip and the 140 kip alerts?
I can try to answer some of that, and Roshan, you might have another opinion. So the 80 kip being the level 2 that I showed on slide 9 is EHMS level 2 or AAR A2. So that is a advisory that offers replacement if they are repaired in a shop for any other reason. So it's different than if it would progress up to 90 kips, then that would be pulled into a shop specifically for that repair, and then the top level 4 mandatory, so 140 would be requires immediate action. So I guess in terms of predicting progression for one or the other, potentially yes, because just because it gets that 80 kip level 2 doesn't necessarily mean that the wheel is going to get replaced right then and there.
Both Farzad's question and this discussion illustrate the opportunistic maintenance practice where a wheel that may have remaining useful life is changed early to avoid a future out-of-service event on the car. And there's a lot of discretion that is exercised when those decisions are made.
I agree. Just a quick point to add to that. So 80 kip is still an alert. It's still a condemnable alert when it is in a shop or a rip track. So if we want to predict 90 and 140 after it hits 80, um, I would say we will lose a bunch of opportunities there. So there is a window open, which is, I believe, 65 plus, right, Dave?
Yep.
So probably that will be a good starting point for any predictive model where it says, hey, this can actually reach 80 in 2 months or after so many miles or whatever it is, right? So I would prefer starting at 65 kip rather than 80 kip. And then just one more clarification. I know that everyone is talking about like WPD, wild, and THD and all those things. It, you all should understand that these are all 3 different um, information. So WPD is completely different from wild or THD. So WPD is wheel profile detector, which means it measures the information of the wheel profile. Is the flange too high? Is the flange thin or rim thin, or is there a tread hollow, right? That is a geometrical information that is uh, calculated by that detector, right? So that's different. Wild is wheel impact load detector, which is vertical impact that the wheel sees. It can be due to someone actually left the handbrake on and the wheel moved. So it forms a flat spot. And that in turn results in a high wild reading, which is high vertical impact reading. Or there might be spall or shelling or whatever it is, right? So that actually increases the uh, uh, opportunities for high impacts, right? THD is completely different, where it's the truck performance. It's not just the wheels, but the truck itself, is it in a good condition or not? And a part of the problem is the wheel. So if it has a hollow wheel, then the truck is going to hunt. So if you are looking at all these data, you need to make sure that in certain cases you need to silo it. In certain cases, you need to figure out if there is a relationship between a WPD and a THD, or wild and a WPD, so on and so forth.
Roshan, thank you.
Thank you.
We have reached 10 o'clock Eastern Time, and we appreciate all of the attendance and the questions that were posed by the competitors. I'd like to close by thanking the TTX team again for the problem and for the discussion today, and invite all competitors to continue to ask questions to your problem co-chairs via the discussion board on the Kaggle competition site. Again, for those of you who have not yet registered for the competition, you have about another week to do it. And I would encourage all competitors to get started and work vigorously to get good answers to this problem. Thank you all for your attendance, and look for the link to the YouTube of this webinar, which will be distributed to all of the competitors who were originally notified of the webinar. Thank you.
Thanks, everyone.
Thanks, Marty. Thanks, everyone.
One.
Bye.
All right. Well done, everybody. Thank you. Bye now.